PhD student submitted. Woo! Right, so star formation-driven outflows are an integral part of the baryon cycle. So we've got gas, it accretes onto a galaxy, it cools and forms stars. Then as part of that star formation process, more gas is ejected out of the galaxy. Some of that may be reaching velocities where it can reach the CGM, the circumgalactic medium, and enrich it. And some will be reaccreted onto the galaxy itself. And so that completes our baryon cycle. Star formation also causes turbulence within the disk of the galaxy. And this is incorporated into this process, which we know as stellar feedback, where it regulates the star formation within the galaxy. And so by outflows, which are driven by the same process that drives that turbulence, are therefore an observational tracer of the underlying stellar feedback. So by studying the properties of outflows, we can better understand the star formation processes. So this is our obligatory picture of M82. This is a local starbursting system. It's probably the best studied outflow system in our universe. But it is just one galaxy. Although it's close, so we can make models based on it. If we really want to understand how star formation works in galaxies with different masses, different metallicities, in different environments, then we really need to be building up a more statistical sample of resolved observations of star formation-driven galaxy outflows. And so this is where DUVET comes in. DUVET is a sample of starbursting disk galaxies in our local universe. They are chosen to be 5 to 15 times the main sequence value. They're compact and they're nearby. So they fit really well into the field of view of KCWI, which is an IFU on Keck. And so we have 27 galaxies observed with KCWI, both face-on and edge-on. Because we have IFU observations for them, this means we have hundreds of sightlines for each galaxy at sub 500 parsec resolution. And so when we're using these galaxies to study outflows, some of them are edge-on, like M82. This means we can look at the disk, then we can look at the outflow separately, see how it changes as you move off the disk, look at things like metallicity, the ionization, and the geometry. And Daniel and Magdalena will both be talking a bit more about this later. We can also use quasar absorption sightlines to study outflows. And Antonia is going to be talking a bit more about how we do this. You can ask her more about that later too. But I use face-on galaxies to study outflows. So this means that we're looking down the barrel of the outflow cone. We can start to relate the properties of the outflows to their underlying star formation directly. So we've got the section of star formation that drove the outflow. We can directly compare its properties to the outflow. And I use these galaxies to answer three main questions. Firstly, how are outflows distributed? Secondly, what mechanism is driving the outflow? So we know that they're driven by star formation, but is it primarily supernovae or is it young massive stars? And thirdly, how do the outflows actually regulate the star formation which is driving them? So firstly, how are outflows distributed? Well, if you've seen me give a talk before, you've probably seen this plot many times. This is IRS 08339 plus 6517. It is our pilot target for DUVET, and when we observed it, we found evidence for outflows across the entire face of the galaxy out to R90. Now, we don't just have IRS 08, we also have the other DUVET galaxies, so we can now start to do that for them as well. So here we have the covering fraction plotted against the star formation rate surface density. So what I mean by covering fraction here is the fraction of spaxels where we find evidence for outflows within R90. What we found is that in galaxies with a higher median star formation rate surface density, they have a higher covering fraction. So this kind of intuitively makes a bit of sense. As you have a higher if you have a higher star formation rate surface density, then you have more stars forming, which is able to give more energy to the gas to drive more outflows, which means more of the galaxy is able to drive those outflows, and we see it more across the face of the galaxy. But we don't just want a two-dimensional view of how outflows work. We want to start studying them in a three-dimensional way. And so usually when we study outflows, we do this double Gaussian decomposition of the emission lines. This ends up with us calculating a single velocity for the outflow in each spaxel. This is a very simplistic assumption. We're basically assuming that all of the gas is moving at one velocity away from the galaxy. And we know that's not really true. If you look at observations and simulations, we know that gas moves at a variety of velocities in these outflows. And so what we've done is we are developing a non-parametric method to measure what's going on in these outflows. So we take the purple Gaussian here, the narrow one, which we assume is flux coming from the galaxy. We subtract that off, and then we divide the residuals into 3 flux bands. So we've got, firstly, in blue, flux, which we assume is coming from gas which is still within the disk of the galaxy. Then we've got in purple, flux, which is moving at mid-range velocities. It's left the galaxy. It will probably be reaccreted. And then we've got flux, which is coming from gas which is moving at higher velocities, which may reach this EGM. So then we can look at an example of how this is working. This is UGC galaxy. It's one of our DUVET targets. And we can look at the flux which is coming in all of these different bands. So we've got mid-velocity gas and high-velocity gas. What we're finding is that most of the ionized outflow gas does not actually completely escape the galaxy halo. Most of it is in that mid-range velocity band. There's also a difference between what we find for O3 and what we find for H beta, and this may have to do with the ionization state of the gas. So now we know how they're distributed. We want to know what's driving them. So this is a plot of the outflow velocity, the maximum outflow velocity, so we're going back to that single velocity again, plotted against the star formation rate surface density. And we have different subgrid physical models which tell us, predict what this relationship should be depending on what's driving the outflows. And we find that our outflows are consistent with being driven primarily by supernovae. We can also look at the mass which is coming out of the outflow and compare that to the star formation rate surface density. And we find that, again, this correlation is consistent with models where our outflows are driven by supernovae. And so you can think about if you have a higher star formation rate surface density in your galaxy, you're going to be forming more stars, which means more supernovae, which means more energy to drive more mass out of your galaxy, which explains this relationship here. And so now that we know what's driving them, we want to relate that back to the star formation which is actually going on in the disk and see how that affects it. So then we can start to put our outflow properties on a plot of the Kennecott-Schmidt diagram, or the star formation law. So here we have the star formation rate surface density plotted against the molecular gas surface density. In grey, you've got main sequence galaxies, so these are spiral galaxies from the Heracles sample. And then the coloured points on top are from Iris 08. And we've coloured them by the mass outflow rate flux. So this is the amount of mass which is flowing out per area. What we find is that, again, as we saw in the last plot, as you move to higher star formation rate surface densities, you've got more mass which is outflowing. But also, as you move from a main sequence to shorter depletion times in starbursting regions of the galaxy, we get more and more efficient at driving the outflow. So this means that outflows are actually regulating the star formation, particularly in these highly efficient star formation regions. They're actually more efficient at driving outflows than they are at turning gas into stars, which is really affecting the way that star formation is regulated in these areas. This limits the time they can have a short depletion time, which means that eventually these starbursting regions of the galaxy will fall back onto the normal main sequence relation. So to summarize, we find that outflows are detected across the entire disk of Iris 08 and many of our other DUVET sample galaxies. We find that our results for these galaxies are consistent with outflow velocities. The outflow velocities are consistent with the outflows being driven by supernovae primarily. We also find that the outflows are removing gas from the disk more efficiently in starbursting regions, but that the majority of this ionized gas is actually going to probably be reaccreted onto the galaxy and it won't escape altogether. Thanks.